Okay, so welcome to one more monthly seminar of the Young Researchers of Quantum Gravity. Today we have the pleasure of receiving Eloise Delaporte. She's working with Professor Astrid Eichhorn in Denmark, in the University of Southern Denmark in Odense. And today she's going to report to us a bit about her PhD work. So thanks, Eloise, for accepting to give us this talk.
Thank you very much for inviting me to give this seminar talk. It's the first time I'm doing so. I hope I will give a broad overview of the field and also some specific works that can be done within it. So I'm going to talk about this particular connection between non-circular black hole spacetimes that are, I would say, inspired by quantum gravity rather than being fully quantum, and their connection to observational signatures. So let me first give you the outline of my talk. In the first part, I really want to introduce you to why we should look at black holes when we want to go beyond GR. And this is both from an observational point of view, but also from a theoretical point of view. And then I will tell you how we can approach black holes beyond general relativity. And then I will talk about, if I have time, 3 different projects that I have been working on during my PhD that all connect to non-circular spacetimes and observational signatures, and then provide you with a conclusion. So first of all, why do we want to look at black holes? Well, we know that if there is any departure from general relativity, this can manifest either at a very large scales, so at cosmological scales, where there are some tensions with the lambda CDM model, or it can also manifest in places where the strength of the gravitational field is very large, namely in compact objects such as neutron stars and black holes. And the fact that we are looking at black holes beyond GR more specifically is because recent observations, such as gravitational waves that have been recorded from neutron stars and black hole binary mergers by the LIGO-Virgo-Cagra collaboration, and shadow images of supermassive black holes that have been derived by the Event Horizon Telescope collaboration, are now pushing the boundary towards near horizon tests of black holes. And that means we can now test general relativity and especially the Kerr hypothesis. And before I explain a bit better what I mean by Kerr hypothesis and why does it matter, let me just say that I will focus only on the observational probe from shadow images, and I will not talk about gravitational wave. So yes, the Kerr hypothesis states that within general relativity, Kerr metric is the unique vacuum, axisymmetric, and stationary solution. And that means that observational constraints that are derived from gravitational wave transient signals and constraints from supermassive black hole shadow images should match, even though they are coming from black holes that are on opposite mass ranges. So gravitational waves are now taken for stellar mass black holes, while shadow images are computed from supermassive black holes. But if you go beyond GR, this uniqueness of solutions might not hold across all masses of black holes. And there have been a recent example that is coming from a work from Astrid Eichhorn, Pedro Fernandez, Aaron Held, and Hector Silva within a specific scalar Gauss-Bonnet theory. And so what they have shown is that at the very low mass range and high mass range of the black holes, the only solution was the Schwarzschild solution. So they only focused on spherical symmetry. While in intermediate mass range that could extend to supermassive scales, there were 2 different branches, one that is Schwarzschild and one that is a scalarized black hole. And therefore, this is breaking black hole uniqueness across a certain mass range. Now let me also motivate why we are looking at black holes beyond GR from a theoretical point of view. And this is coming from the fact that classical general relativity breaks down or predicts its own breakdown in different ways. Namely that black holes within GR are plagued by curvature singularities in their center. And at least for stationary black holes, those suffer from geodesic incompleteness. So you cannot extend the geodesics beyond a certain point in time. Moreover, black holes form through gravitational collapse, and a simple classical model of gravitational collapse can lead to an X singularity. And finally, many black holes possess a Cauchy horizon, which imply the existence of closed time-like curves, and could also trigger a mass inflation instability. And so the idea with going beyond GR is that if you introduce new physics that is either classical or quantum, by introducing this new physics, those can partially cure the singularities that are present in the classical case. And this occurs often by weakening gravity as we go towards the center of black holes. And therefore, in the past years, there have been growing efforts in developing modified gravity theories and also quantum gravity theories that could connect to observations in the strong gravity regime where black holes lie. So the main broad question that we are trying to address is how we can test GR and alternative theories with observations with black holes specifically. So now let me tell you how we can approach black holes beyond GR. There are 3 different ways where you can follow. And the first one is the principled approach, also called fundamental, where you pick your specific theory beyond GR. So that can be specific quantum gravity theories or modified gravity theories, whatever you want, that has new fundamental degrees of freedom or new symmetries. And then by solving the equations of motion, you derive a black hole solution within each theory and state their properties. But in practice, this is unfeasible. First, because solving the equations of motion beyond Einstein field equations is notoriously difficult. And secondly, because you would have to repeat that for every theory beyond GR that you have at hand in order to have a complete picture of the black hole solutions. So you can follow a completely different approach, which is the parameterized approach, in which you remain theory agnostic, and you just parameterize deviations from a GR at the level of the metric. And this parameterization then can be constrained observationally, for example, through black hole images. And why this is comprehensive, because most of the parameterization here include solutions that have been derived in fundamental approaches. It is disconnected from fundamental physics, so it's very hard to link these deviations to the new fundamental degrees of freedom. And finally, you can follow a middle ground approach that is trying to take the best of the 2 others, in which you still parameterize deviations from GR, but you motivate those deviations by following new physics principle. And this approach has been developed by Astrid Eichhorn and Aaron Held in 2021. And this approach is especially nice by combining the 2 others, and also because it can lead to regular black holes, so black holes that are free of curvature singularities. And that's the approach I will focus on first. So let me explain a bit more in detail what are the new physics principles in this approach. Well, the first thing is that we want to recover the correct Newtonian limit when going to large R. So we know that the only quantities that define black holes are mass and spin that are constant. at least within GR. That's what we observe. And therefore, we need to recover those at large R. We also want to ensure regularity. That means the spacetime should be free of curvature singularities everywhere. We follow locality, so we implement locality, and that follows from an effective field theory reasoning, in which you expect deviations from GR to become more important when the local curvature grows. So the local curvature of your spacetime. And finally, you also implement simplicity, for which new physics only come with a single scale and not several. And following this principle leads to a certain class of spacetime metrics with a certain form, in which modifications occur by upgrading the usual constant mass from the Kerr metric to a mass function. And the specific form of this mass function is chosen such that you satisfy the four principles. And in particular, when you want to satisfy locality and simplicity, your mass function should only depend on the radial coordinate through this particular factor. So K is the local curvature, and R and P is the new physics scale. And you can also, instead of upgrading the mass itself, you can upgrade the Newton constant G0 to its running counterpart. For example, its running counterpart coming from asymptotic safety. And therefore, the running counterpart should only depend on the running scale and omega, which is linked to the value of the fixed point. And you identify the running scale K with the local curvature. And once you have your mass function, you make sure that the upgraded spacetime satisfies the correct Newtonian limit, and that all the curvature invariants are finite everywhere. Okay, so now let me move on to how we can apply this principle-parameterized approach to gravitational collapse. So as we know, astrophysical black holes, the black holes we observe, must form through gravitational collapse. But it turns out that simple classical models for gravitational collapse have failures. And this is a case of this the simple example I want to review, which is the Vaitia-Kuroda-Papapetrou model. This model describes the spherically symmetric gravitational collapse of null radiation. And it is given by this metric. So you have an angular part, and due to the symmetry, this will not be very interesting for us. So we will focus on the radial and advanced time part. This is the time-dependent metric because you describe gravitational collapse that is dynamical. And your mass function is time-dependent and linearly growing until it reaches a certain constant value and settles down to a Schwarzschild black hole. And already at the classical level, the spacetime has a curvature singularity in the center, and also in negative singularity for a small enough value of the accretion rate. So the accretion being mu. And moreover, it satisfies the null energy conditions, which through the Penrose-Hawking singularity theorem implies that the spacetime is geodesically incomplete. So the question we're asking is, if we apply the principle-parameterized approach to gravitational collapse, can we solve or can we cure the singularities that were found in classical? And let me come back to the metric before. So it had a curvature singularity in the center, and therefore a necessary condition, but not sufficient, to cure this curvature singularity is to add a radial dependence in the mass function. And so that's why we consider a generalized Vaitia metric, where now the mass function has an additional radial dependence. This generalized validity metric corresponds to the gravitational collapse of null radiation and null fluid. And we upgrade the mass, so we choose the specific form of the mass such that it satisfies our 4 guiding principles. And you can see that indeed the radial dependence only comes from this k times r and p squared term. So it satisfies simplicity because there is only one new physics scale, and it satisfies locality. And of course, all the 2 others. We check that the upgrading collapsing black hole is more compact than its classical counterpart, and that is at any time. And this results from the weakening of gravity that is necessary to regularize the spacetime. And a specific case of this mass function is found to correspond to the asymptotic safety inspired upgrade, which, as I described earlier, you don't upgrade the mass itself, but you upgrade the Newton constant to its running counterpart coming from asymptotic safety. So by construction, our spacetime is free of curvature singularity, so it's regular. Of course, it has an even horizon because it's a formation of a black hole, but it also has apparent and inner horizons, which are represented here. So the apparent horizons is in dashed lines, and the inner horizon in continuous lines in function of the new physics scale. And so you can see that for a large range of new physics scales, both coexist until a certain critical value of the new physics scale, which is represented by this dot, beyond which they merge and the spacetime become horizonless. And if you compare the left plot with the right plot, you can see that the critical value for the new physics scale increases with time. And that basically means that for a certain new physics scale that is large enough, there can be new physics effects that are not hidden behind an horizon. So if you take an initial time that is small, then the critical value is also small. And therefore, you can find a new physics scales for which the new physics is not hidden behind an horizon. And additionally, we computed the null energy condition and found that it was violated in some regions of spacetime and parameter space that are represented here in color. And this seems to indicate that the spacetime is geodesically complete. And in order to gain further insight into geodesic completeness, we studied the null geodesic motion in the spacetime. So null geodesics are represented in phase diagram in terms of R and V. And we compare the classical trajectories with the upgraded trajectories. So the classical trajectories are given by the continuous gray line. And you can see that they reach the center r equals 0 in finite time. While for the quantum or the upgraded spacetime, the geodesics seem to reach a specific trajectory in blue here. And therefore, this indicates that the spacetime seems geodesically complete. But the fact that the geodesics get trapped to a particular trajectory, which corresponds to an inner photon sphere that is stable, this can trigger a mass inflation instability. So no energy coming from these photons can pile up this specific trajectory and triggers an instability. Let me also mention the limitation of this study, namely that we only focused on spherical symmetry, and we only focused on null geodesic motion, while in order to have a proof of geodesic completeness, you would have to study also time-lag geodesics and potentially also non-geodesic trajectories. And furthermore, we only performed a numerical study because we could not find an analytical solution for the geodesics. Okay, so let me move on to another approach. So I talked about the principled-parameterized approach here in the middle. Now I want to focus on the parameterized approach. And this is a work that focused on symmetries of parameterized metric of black holes, and especially how you can go beyond circularity. And this work started by realizing that existing parameterization in the literature assume one or two symmetries, which are circularity and sometimes also hidden constant of motion. And what are those two symmetries? So circularity is given by this condition here, and therefore it corresponds to a restriction of your Ricci tensor in the Killing directions of your spacetime. And it is a true spacetime isometry in the sense that it does not depend on the choice of coordinates. But if you choose specific coordinates, it can take a simple form. And this is the case for Boyer-Lindquist coordinates, where circularity, where a metric is circular if and only if it is invariant under the simultaneous transformations t goes to minus t and phi goes to minus phi. Now, if your spacetime is circular, you can also have an additional constant of motion that is constructed from a rank 2 Killing tensor in this way. And this does not put restriction on the spacetime itself, but on the particle's motion in this spacetime. And explicitly, it implies the separability of the geodesic equations. Now, let me show you how these symmetries impact the form of the metric. So if you start from any metric in 4 dimensions, this has 10 components. And if you consider the usual symmetries that are axis symmetry and stationary, this can reduce the metric components from 10 to 6. Now, if you add circularity, then the number of metric components is further reduced to 5. And this is clearly visible in the form of this metric, which is the most general circular metric that you can write. And this has indeed 5 metric components. And this is also invariant under t goes to minus t and phi goes to minus phi. So whenever you have such a metric and such invariance under t goes to minus t and phi goes to minus phi, your metric is circular. And then additionally, you can add a constant of motion. And why this doesn't change the number of metric component, it has an impact on the free function, because now they only depend on one coordinate at a time. And therefore, this forms a subclass of the circular metrics. So why do we care especially about circularity? Well, in general relativity, circularity trivially holds because all vacuum solutions are Ricci flat. But when you go to a non-vacuum GR, for example, if you have some particular magnetic field and also beyond GR spacetimes in scalar tensor theories, those spacetimes have been shown to break circularity. So it is important to come up with a more general and non-circular spacetime parameterization, which we have written down here, and it's in horizon penetrating coordinates. So every parameterized deviations is encoded in this delta function that depends both on the radial and the angular coordinate. So whenever these delta functions are 0, you recover the Kerr metric. But when they are non-zero, and in full generality, this parameterization is non-circular. And it reduces to circular spacetime upon specific conditions on the delta function. And for us, the interesting point is that this non-circular parameterization includes regular black holes. And those regular black holes are obtained from Kerr by turning the mass into a mass function, as I mentioned before. And this mass function can either depend solely on R or on R and angular coordinate. And the first one leads to a regular circular spacetime, and the second one to a non-circular spacetime. And this non-circular spacetime seems to have specific black hole image feature. So if you take this black hole image feature, black hole image, and you focus on the prograde side of the image, so if you zoom on this part, you will obtain the two other images. The one in the middle corresponds to a non-circular spacetime, and the one on the right to a circular one. And you can see differences, namely that the non-circular spacetime shows cusps, both in the shadow boundary and in the photon rings, and also a dent in the y=0 axis. And therefore, this motivates the search for non-circular image features with the next generation event horizon telescope to determine whether circularity is a true symmetry of black holes or not. Now let me move on to a more, to make the connection with the observational signatures of black holes. So as I mentioned in the very beginning, we have mainly two probes, two observational probes, gravitational waves and black hole shadow images. And if you consider black hole shadow images, those are formed both by the direct emission from the accretion disk around black holes, which is represented here. But here you can have particles that emit photons, and those photons reach directly the observer. And you also have photon rings that corresponds to lensed photons. So photons start orbit the black hole a certain number of times before reaching an observer. So in this picture, you can see the different photon rings labeled by an integer. So n=1, n=2, n=3, and so on. And higher order photon rings, so those that have a n that is larger or equal than 2, are a clear probe of spacetime geometry. And this is because they are lensed more and more, and therefore closer and closer to the shadow. This is why it is interesting to look at photon rings beyond GR. And it has been realized that there are some generic features of these photon rings beyond GR. So in general, they are more widely separated than GR black holes. And you can see by comparing the first set of images with the second set of images. So the first set corresponding to a parameterization of a black hole beyond GR. And the second set is a Kerr black hole. And you can see that the photon rings here are more widely separated than in the Kerr case. And also the photon rings have similar flux densities. So they are almost as bright. So the second photon ring is almost as bright as the first, while in GR, the photon rings get fainter as they go towards the center. So, but you can also see that if you lower the resolution, so if you basically blur more and more your image, these differences between GR and non-GR tend to get washed out. And therefore, it motivates a study of what current and future radio telescope arrays are able to do. So whether they are able to detect two photon rings and disentangle them. And in order to have to do such a study, we created synthetic images with either one or two rings that we modeled with flat flux profiles. So we use simple geometric models to represent the one or two rings in our images. And our models has this set of parameters. And we keep the total flux density in the image and the diameter of the outer ring constant. And the values are motivated from M87 observation. And we vary the other parameters, namely the separation S between the two rings, the width of the rings, and the relative flux density. So that's the ratio of the flux density of the two different rings. So then once we have our synthetic images with different types of separation, different types of relative fluxes, we want to see how they are observed by radio telescope arrays. So we either consider the current EHT array with sites in black in this map, or proposals for next generation EHT arrays that are in red and magenta in this map. And you use this to input data in the EHT imaging tool that have been developed by Andrew Chell. And what this tool does is to perform a mock observation and apply a Fourier transform to the data to give the Fourier data, the corresponding Fourier data of the image. And the Fourier data of a flux profile is given by the visibility amplitude. So the data that you obtain from this image seen by these arrays is given in black in these plots. And what we do then is to fit this data with two different models, one that only has one ring and one that has two rings. And the goal is to determine when and where those differ. And you can already see that with next generation EHT arrays, you start to see a difference between the two fits. But we need a more quantitative measure of these differences. And for that, we compare the two fits with a two-sample statistical test, which outputs a p-value. And so whenever the p-value is close to 0 down there, the two different fits are coming from two different distributions. And this tells us that the two rings are disentangled. While if the p-value is close to 1 here on the top of the plot, the two fits come from the same distribution and there is no way of disentangling the two rings. And so we did that for different values of separation and relative flux. So we performed scans along these black lines in our parameter space, and for each different array. And you can see in these plots that some arrays that are the future NG-EHT arrays are performing much better at disentangling the photon rings than the current EHT array. So I mentioned the visibility amplitude, which is this V here, which corresponds to the Fourier transform of the initial image profile. But actually the measured visibility amplitude is plagued by some systematic uncertainties contained in these G factors, and also thermal noise contained in this epsilon. And therefore, this tends to increase the value of the visibility amplitude. And in order to get rid of this gains factor, you can define new quantities that are the logarithmic closure amplitudes, such that they are independent of the gains. So you remove the systematic uncertainties. And these closure amplitudes have 4 indices because they are defined for each set of 4 radio telescopes. And now you can do the same as before, so the same as we did for the visibility amplitude, but you can do it for the logarithmic closure amplitudes. So you basically compare the one-ring model and the two-ring model in this quantity. So the blue being the one-ring and the red being the two-ring. And the peaks here in these figures tell you about the shape of the rings, so the flux profile you chose. Why the shift between the two, the blue and the red peak, gives you an idea of the how you can tear apart the two photon rings. And the image on the left was obtained by an ideal square array of radio telescope, while the image on the right has been obtained with only 4 stations, but 1 station was put in space. Okay, let me quickly summarize. What we have found is that if you consider the current EHT array, which is whose parameter space is given here, you can only disentangle the two rings if they are widely separated, here in green in the lower part, or if their relative flux densities are very different. But we expect further improvement if we add new telescopes on Earth with a high sensitivity. Then you can probe much more of your parameter space and disentangle much more the photon rings. Or if you use super resolution techniques, so that is, for example, restricting the width of your rings. Or if you add a space-based telescope where you can probe much smaller scales in your image. Okay, I'm now coming to my conclusion. Let me summarize what we have seen. So, as I mentioned, circularity is often assumed in parameterization of black holes beyond GR, but it does not need to hold, so we shouldn't assume it. And this is why we came up with a non-circular parameterization of black holes. And this non-circular parameterization leaves specific imprints in the black hole shadow images. We also asked the question, can we disentangle the two photon rings with current EHT array? And the answer is only for large relative flux densities and large separations. But you can improve that. You can have a better disentanglement if you use super resolution techniques, if you add new telescopes on Earth with a high resolution and high sensitivity, and if you add a space-based telescope. And finally, we have also seen that applying the principled-parameterized approach to spherically symmetric gravitational collapse seem to be able to resolve the problems of the classical gravitational collapse because we can obtain a regular black hole, and this regular black hole seems to be geodesically complete. But the problem is that we are left with a potential mass inflation instability. So I would like to thank you, and I'm open for questions.
Thank you very much, Elise, for the very nice talk.